Hi everyone, today we'll learn what supervised machine learning means. In supervised learning, we have input-output pairs. The computer learns a function that maps each input x to its output y. We call this f of x equals y plus some noise. Our example, BMI is x and the diabetes risk score is y. In supervised learning, we have input-output pairs. The computer learns a function that maps each input x to its output y. We call this f of x equals y plus some noise. Our example, BMI is x and the diabetes risk score is y. Every supervised learning task has three parts: a dataset with inputs and targets, a learning algorithm that trains the model, and a predictive model that can make new predictions. Data plus algorithm equals model. Let's look at a small dataset of patients. Each patient has a BMI and a diabetes risk score. Our goal is to find how BMI affects the risk and then predict new patients' risk automatically. Here's the math view of a dataset. We have many pairs xy. Each x can have several features and y is the target. We put all x values in a matrix X and all y values in a vector. The model will use x to predict y. Attributes are what we measure, like age or blood pressure. Features are what we use, maybe normalized or transformed versions. Features are how we describe the data to the model. Here we see how BMI values are spread in the dataset. Most patients have BMI between about 20 and 30. This scatter plot shows BMI on the x-axis and diabetes risk on the y-axis. You can see the higher the BMI, the higher the risk. A clear positive trend. In Python, we load the diabetes dataset, keep only the BMI column, and view some sample data. This helps us understand what the data looks like before training. A learning algorithm has two main parts: the model class and the optimizer. The model defines the line we want to fit. Y equals theta, 1x plus theta 0. The optimizer finds the best values for theta 0 and theta 1 so the line fits the data. Changing theta 0 and theta 1 changes the line's intercept and slope. You can see how different parameter values produce different fits to the data. Earlier, we saw the model class and optimizer. The missing piece is the objective or loss function. It tells us how wrong the model is. The optimizer adjusts theta to make this loss as small as possible. This diagram shows the full process. The model class creates predictions, the objective measures errors, and the optimizer updates theta repeatedly. When the loss stops improving, we get the learned model f hat theta of x. In linear regression, we assume the relationship is straight. F theta of x equals theta 0 plus theta 1 times x. For more features, we just add more terms. The loss function tells us how far predictions are from actual values. We'll look at two types: mean squared error and absolute error. MSE squares every prediction error, so big mistakes count a lot. It's smooth and easy for optimization. If the prediction is far off, the loss increases quickly. The model learns to reduce big errors first. L1 loss takes the absolute value instead of squaring. It treats all errors more evenly and is less affected by outliers. If one prediction is very wrong, it doesn't dominate the whole loss. Here we compare both with the same data. MSE gives a higher number because it squares large errors, while L1 gives a smaller average. It's more forgiving. The blue curve is MSE. The orange line is L1. Notice how MSE grows faster, steep curve, while L1 grows linearly. This is why L1 is more robust to extreme values. Now we need to find theta values that minimize the loss. In scikit-learn, linear regression does this automatically by solving a least squares equation. The optimizer tries to find theta hat, the best parameters that make loss smallest. Think of walking downhill until you reach the lowest point. That's your best theta. Here's a curve showing loss versus theta. We start high, take steps downhill, and stop at the lowest point, the minimum. The optimizer updates theta a little each time. In these Python cells, we load the data, split it into train and test sets, train a linear regression model, and compute the mean squared error. We see how code follows the same logic we learned in the slides. The yellow points are real data, and the yellow line is our model. You can see it roughly fits the pattern: higher BMI, higher risk. Instead of using only BMI, we can add more features like blood pressure. The model becomes multidimensional, and MSE can improve if these features add useful information. Try repeating the experiment with 2 features, BMI and blood pressure. See if your test MSE improves. This helps understand model complexity. You can explore the original Cornell Applied ML notes and scikit-learn documentation to learn more.